So today I will be showing you how to use my custom ITC data analysis functions included in my MetaboMgITC package. If you haven't already done so, please watch the help video tutorial that shows you how to set up the program on my GitHub page. So the first thing I'm going to do is I'm going to open an R script and set up the program. And basically to do that, you just have to type DevTools, load all. Okay. And this will expose all of the functions I'm going to use to your memory and make data analysis a little more facile. The next thing I'm going to do is find the data. You're going to want to save it in this directory somewhere. I have some data already saved. So list.files. And it's saved in this ITC data folder. Okay. And we're just going to look in this folder real quick to see what is there. So I think that I want to analyze my ATP data again. And the first thing I need to do is read the data for the ITC run for the blank and ITC containing the ATP. So the first thing I'll do is make a data frame, call it DFM. We'll call it DFATP. And we're going to use read.ITC. And then actually, I'm kind of forgetting how this function works. So I'm going to use question mark read ITC. I wrote it, but I've forgotten how it works. Good thing is I wrote some help implementation, and you can use question mark to pull that up. And I see that it has one important argument, file concentrations. So file.concentrations. So this is where we're going to tell it what file to use and what concentrations there are. So we'll make a vector C like this. And the first thing we need is the path. So the file is ITC data. And the ITC file from MyCoCal for ATP is going to be, let's see here, this one right here. All right, so I'm just going to copy the file name. I'm going to put it here. And my the next part of this vector I need is the syringe ligand concentration, which is 0. Wait. Actually, this would be the syringe magnesium concentration, which will be 15. Says it right here in the file name. Next is the syringe macromolecule concentration, in this case ATP, going to be 0. And sometimes you want to do some competitive ITC. This is not an example, but you might have some competitor in the syringe. But in this case, there is none. So that's also 0. Now we can move on to the cell. The cell contains no magnesium. It contains 0.2 millimolar ATP, or 200 micromolar, which it says in the file name. It contains 0 competitor. And then I should be good to go. So I don't have a dependent package downloaded onto my R console for this computer. I normally code on a different computer. So I'm just going to install that real fast. So I'm going to use install packages pragma. And hopefully this will go quickly. So it's done. It's downloaded this package. And now if I run my function, it works perfectly. So it read it in to an object. So it is composed of the delta power, the raw data, and the heat per injection, dq dx, and it also has the concentrations of each injection. We'll do the same thing for the blank. So we'll call this df blank. And once again, I need to search for the data file, and it's this one. And I need to rename, make a new object called df blank. And just finished reading that in for us. Okay, after that, we can use a function that's named for the package, MetaboMgITC. Just rendered the help documentation. So it's going to fit it to a Weissman isotherm and give us the thermodynamic parameters and binding constant. Everything you would normally get from an ITC data experiment, from an ITC experiment. So to run that, I'll make an object called fit is equal to MetaboMgITC. And the first argument is the cell. The second argument is the blank. So the cell is df.atp. The blank is the df.blank. Run. Now I should be able to run it. It might take a second. And it's done. It fit it good. So you can see N is the stoichiometry of binding. We have the temperature of the experiment. We have the binding affinity constant. We have the saturation of the experiment, which means how many ATP molecules are binding magnesium at the end of this experiment, and it's 97.72%. We have the delta G, the delta S, and the delta H in kcals per mole. We might want to look at the results, so fit. We'll just run it. And you can see it made a rather nice plot. So up top, we have the standard raw data, delta power curve. And then we have the data that's been fit to a line down here. And we can save it. And then finally at the bottom, we have a table of results. I'll just show you how to save the results in case you need them later. The first thing we'll do is save the figure. So to do this, we'll need ggSave. So we need ggSave. It's in the tidyverse. I know that. So I'm going to load tidyverse into my memory, and it's taking a sec. Okay, it's done. Now type ggSave. And then the file name will be example itc.png. And if we go to our directory, where is it? Oh, here it is. It's going to take a second because my computer is slow. And now here we have it. This is the picture that you can use, later. And of course, you can change the thickness, the width and the height, and the dimensions using ggSave. But that's not the purpose of this video. Up next, we're going to save a table of the raw data as a CSV file. So we'll go write.csv, And then the object is going to be fit table. We want to save the table, not the plot. If we run this, we can see it in our console. You see we got the parameter, we got the number, you know, whatever. And we want to save it as, let's go example ITC.csv. And then I'd like to do row.names is equal to false. Okay, now if we jump in here, we've got our example ITC file. And here it is, all the parameters so you can use them later. And so yeah, that's how you use my ITC fitting software.